So just like with gravitational fields, you will find some of this information very familiar. Electric fields are very similar in a lot of ways to gravitational fields. Let's start with some revision. Do a little bit of research and define the electric field. Describe the electric force between two masses. State in what direction the electric field acts. Define electric field strength. State if the electric field strength is a vector or a scalar, and show how you would represent the field around a charge in a diagram. Hopefully you remember this. Electric fields happen because particles have a charge, Q. That Q can be positive or it can be negative. Wherever these charges are, there will be an electric force acting, and that is the electric field. An electric field exists where a charge experiences an electric force. To find the actual value of this electric force, you would use Coulomb's law. Coulomb's law states that the force is proportional to the charges, the product of the charges, and inversely proportional to the distance from the centre of the charge squared. The constant of proportionality is 1 over 4 pi epsilon naught, which we can simplify now to be the Coulomb constant, Coulomb's constant, Ke, which is equal to 8.99 times 10 to the 9 newtons meter squared, coulombs to the minus 2. The direction of this force acting depends on the charges involved. They can be attractive or they can be repulsive. The direction, which we'll look at more closely in the field diagram, would be the direction that a point positive charge would feel at that position. So you always have to consider a point positive charge in order to be able to draw your arrows. The electric field strength, just like in gravitational theory, is the force per unit charge. So we would take our Coulomb relationship and we would divide it by the charge of the particle that is placed in the field. So expressing that same formula as this form, which is exactly the same, but does differentiate perhaps in magnitude. We divide by Q to give the electric field strength as K Q over R squared. Both electric field strength and the force are vectors, so the direction is important. Field line diagrams, as just mentioned, show the direction that a point positive charge would feel in the field. They would be attractive as approaching a negative charge and repulsive if in the field of a positive charge. In radial fields, we would be doing exactly the same as in planetary gravitational fields by drawing lines to the center of the spherical object. However, there is something additional to consider with electric fields, and that's what happens when we have uniform parallel plate fields, where one of the plates would be positive and one would be negative. In that situation, you would have a uniform field, not a radial field. That uniform field would show lines that are equally spaced and perpendicular to the surface and parallel to each other. There would also be some curved lines along the outside as the field no longer becomes uniform. Defining the potential energy of a particle in a field. The definition is exactly the same as in gravitational fields. The potential energy of an object in a field would be equal to the work done in bringing that field, or charge in this case, of a system to their present position, assuming they were originally at infinity. Okay, so the potential energy that this charge has in this repulsive field is equal to the work done in bringing it from someplace outside the field, or the influence of the field, which we will term infinity. So let's define our relationships now. In placing the charge at this point, we are doing some work, and work, as you know, is force times distance. We will use that distance r, and so we end up with the Coulomb constant, Q r squared times r, which gives us our relationship, which once again you should be able to see parallels with gravitational field theory. Oops, I forgot a little q there. Okay, so there we go. The electric potential is very useful in defining what's going on in the field without actually considering the charge q of the object inside the field. The electric potential at a point is defined as the work done per unit charge in bringing a small positive test charge from infinity to that position. Now, what's really important about this definition are obviously the work done per unit charge, but also this point, positive test charge. It's important that you include that in your definitions for all of these electric fields formulas. Right, so what we've got here is potential is our energy over charge, and our energy from our previous derivation is K charge 1, charge 2, R over the charge of the object in the field, which, if we cancel those out, we end up with K Q over R. And that gives us our potential energy per unit charge. So note that both of these relationships are on the data booklet for potential energy and for electrical potential. Now this form is really interesting because you've actually come across it before. The energy of a particle in a field is equal to the charge times its potential difference. Now Q on an electron would be E, which is 1.6 times 10 to the minus 19. So really we're just looking at this relationship, energy equals EV, which we've definitely seen before. And this is probably the form in which you're more likely to use it. So as well as having E equals K Q over R squared, bear in mind that this is also very, very likely to come up as well. So in this question, we have an electron moving between two different potentials. At 12.7 and 15.3, we see a change in potential energy per unit charge of 2.6 volts. Energy equals QV. So our answer for the number of E volts, which is actually easy, I don't know why that's the second part of the question, is 2.6 E volts. And then if we multiply that 2.6 times 1.6 times 10 to the minus 19, we would get the number in joules, which is 4.2 times 10 to the minus 12. How much energy is gained by an overall charge of 2 coulombs when it passes through a battery of 12 volts? Again, we're looking at E equals QV. 2 times 12 equals 24 joules. A charge of plus 4.5 is moved from a place where the potential is plus 2.3 to a place where the potential is minus 1.44. How much energy is transferred? Now here it's important to note that energy is a scalar. So we go from minus 1.44 to 0.23. The difference there is 1.44 plus 0.23. So 1.67 volts is your total potential, and you multiply that by 4.5 coulombs, which gives you 7.5 joules. Is the work done on the charge or by the charge? Well, the charge ends up in a place which is minus 1.44, which means it's a negative charge. It's a positive test charge. You can see there's a positive there. So it's the charge that's moving towards. It's attracted to, so the work is done by the charge. If the charge had been a negative charge, then it would have felt a repulsive force, and the work would have had to have been done on the charge. So that's a tricky question, an important one to consider. Equipotential lines in electric fields do exactly the same as in gravitational fields. They show lines of equal potential. They are always perpendicular to field lines and also show decreasing potential energy. The lines are closest where there is greater potential energy because the jump from one interval to the next is going to be smaller. Here you can see the equipotential lines in a uniform field. For the parallel lines, we're just getting some straight parallel equipotentials which curve as we see the curving out field lines. These field patterns must be learned off by heart. They're very common in multiple choice questions. Have a go at trying to draw equipotential lines around the following. Remember, they're always at 90 degrees to the field lines, and they get closer where the field lines are closer. Remember, closer field lines show stronger field strength. So now might be a good time to review what we've got so far and look at some other bits and compare with gravitational fields. So here we can see all four formulas together. You have force, and then force per unit charge, which is electric field. So we get from here to here by dividing by charge. Our electrical energy, our potential electrical energy is KQQ over R, and we divide by Q, the charge in the field, to give us the potential, which is KQ over R. Now, let's have a look at what happens in this direction. Here we're considering force times distance to give us our energy. Now, why isn't it minus? With electric fields, it's a little bit more complicated because we need to consider the charges. This is something you will deal with in each individual question if there's an attraction or a repulsion, if work done is on the charge or if work done is by the charge. When we get to some questions, we'll have a look at this in more detail. So just like with gravitational fields, we are looking at here an integral. If the force times the distance will give us our energy, then if we do a couple of mathematical derivations, which we don't have time for and we don't have to do, basically what we're looking at is the area under a graph. Similarly, in a graph of energy over distance, we would be looking at the gradient. The relationship between electric field strength and potential is exactly the same. Our potential gradient, which would be the change in potential over the change in distance this time, would be equal to the electric field, exactly the same as in gravitational fields. So our gradient here would give us electric field strength. And in the other direction, similarly, an area of an electric field graph would give us the potential. Now, these concepts are more commonly found in gravitational questions, but it's worth showing the parallels just in case. So this is what your equipotential lines look like for same charges and for attraction for different charges. So it's important now to consider what happens inside a hollow charged sphere. So it's something you might find in a multiple choice question. Now inside, you just have to remember the following. The electric field strength is 0 and the potential gradient is 0, 2. Now the potential gradient, remember, is the change in potential over change in distance. So that change is 0, so it's constant. And because the potential gradient is equal to the electric field, then that would give you a 0 electric field strength. This is sometimes comes up in multiple choices and is not particularly important, but it's just easy to remember. It's just a little factoid to hide away in your brain somewhere. Let's have a quick look at electric fields inside a uniform field plate. We have, the actual maths is actually a lot more straightforward, okay? But just to remember, a uniform field would have a positive plate of a certain value, and it would have a negative plate of a certain value. The electric field strength is the voltage over the distance, but remember there was two relationships for this. There was V over D, but it's also the force per unit charge, the definition of electric field strength. So it's very common to find that you have to use these two formulas in conjunction. So for a charge in the field, the force acting per unit charge would be equal to the voltage across the plates divided by the distance. Now the energy involved would be using QV. The charge times the change in potential. So energy here in the field, again, we're not using, in the electric field, we're not using a radial field, so we would not need to look at these ideas. We're just going to look at what's happening in terms of the charge times the voltage. Similarly, your voltage, you would just use this relationship to find your potential. So V equals the energy over the unit charge. Okay, so we only need to consider these relationships and these relationships. Electric field strength, energy, and potential. Now I'm just going to outline a particular application of uniform fields, which is really outdated now. These electron deflection tubes used to be basically what functioned behind those huge, great big television sets that had the humongous back to them, like that. You might find them in your granny's house, I don't know. Huge, great big televisions. And what they had in here is a cathode tube. And they used a uniform field to accelerate electrons so that they'd basically highlight a little screen here. They're still on the syllabus, but there's no like very common applications for it in everyday life, so I'm not sure how likely it is to come up. But let me just show you the principles just in case. Okay, we have a heating element here, and what this heating current does in this wire is it excites some electrons, and excites them a lot. So they're pretty much just loose, hanging out on that wire, ready to be attracted by something. Now here you can see an anode, which is positive, and what that does is that attracts and rips apart or rips away those electrons from that wire. So they accelerate through to the anode. They all go flying. So those electrons hit that anode, but there's a little hole here. So the electrons that hit that space, that little hole, will come flying out and give you a tiny little electron beam, like that. And what you'd end up with is a dot on the fluorescence screen here. Fluorescence is basically just a coating that will give off light when a charge hits it. So here you get a little dot, which isn't very useful. What you want is that dot to move. So here is where your plates come into it. Because remember, that's what we're talking about. We're talking about parallel plates. So you can get this dot to move. Remember, this is just a beam of negatively charged particles. So if you make this plate positive, then that little electron dot would move upwards. And if you make the bottom plate positive, then it will move downwards, etc. So here is your uniform plate application. You've got electrons moving inside plates, and of course you've got to be careful about the kind of physics that you're using, because if it's moving in this direction, you've got a particle which is negative moving but experiences a force perpendicular to it. So let's say this is a parallel plate and this is a negative plate. If this negative charge feels a force down, what field of physics are we talking about? We're talking a particle moving and experiencing a force which is at 90 degrees to it. And that is, can you think of what it is? It's circular motion, isn't it? So bear that in mind, because they do sneak that in as well. So let's try some questions in this context. You have a 2,500 volt electron gun to produce a beam of electrons. What is the kinetic energy of each electron emerging from the gun? Well, straightforward. You have 2,500 volts. And the charge is 1.6 times 10 to the minus 19, because we're talking about electrons. What is the kinetic energy? You multiply those, and you end up with 4 times 10 to the minus 16. Now, if that is their maximum kinetic energy, we can then find their maximum speed by using the mass of an electron, which is in the data booklet, 9.1 times 10 to the minus 31, and rearranging to find V as 3 times 10 to the 7.